Okay, so today we're going to talk about molecular structure and how to define molecular structure. So for many of your molecules, this will be difficult to do, I'd say, with pencil and paper. But knowing how to pick particular coordinates in your molecule, like a dihedral for this giant borane thing, you will still be able to do that. And even in the CHEM's case, where you've got 250,000 atoms, if you get into the highest level of calculus, are you doing anion? Are you doing
No, we're not
QM,
doing
MM? Okay.
Well, I'm doing it separately, not in the same calculation.
Okay, so when you get to the QM part and you want a particular bond angle or bond length or dihedral, most of the time it's the dihedrals we're concerned about. Today's lecture is going to be critical for you to figure out how to designate the active coordinate that you want to manipulate. Okay, but first let's talk about the Z matrix. Wow, look at that.
Oh, yeah.
That was funny.
It's over there.
Sorry. I don't know how I got the name Z matrix. It's really, I don't think it's really a matrix. But so let's build hydrogen peroxide. Okay? It's such a small molecule, we don't need GaussView. Right? We can just build hydrogen peroxide using the Z matrix. Okay? So H2O2, let's start with atom 1. Okay, so we'll do 1, 2, 3, 4. Those are our 4 atoms that we're going to use, and those are the labels. Okay, now that's not a great structure. Okay, so let's use the Z matrix to make a more realistic structure for H2O2. So the Z matrix starts out with atom 1. And so we're going to call that hydrogen. And Gaussian, when we start out, or you might think of it as the Z matrix, it's just going to stick that at the origin. So we don't need to tell the software anything about that molecule or that atom. It's just the first atom. It's going to be at the origin. Okay. The next atom is oxygen, and we need to put that somewhere in space. And I'm going to go put the numbers there too. So H1, O2. So where is that one in space? The only thing in space is that first hydrogen. And so we're going to pick a distance from that hydrogen. We first need to tell it it's bonded to that hydrogen. So it's bonded to 1. Okay. So O2 is bonded to atom 1 with a certain distance. We'll just round these down. We'll say it's 1 angstrom away. It doesn't have to have a digit here, but I'll say, I'll do this. It must have at least a decimal. You have to tell Gaussian where the decimal is. Okay? If you just put a 1 there, it's going to say, I was expecting a floating point number and I got an integer. So you need to tell it that it's a floating point number, and the easiest way to designate a floating point number is to tell it where the decimal is. Okay. And so this is saying hydrogen 1 at the origin, oxygen 2 bonded to hydrogen 1 at a distance of 1 angstrom. So this means bonded to 1, atom 1. And this is distance in angstroms. So now we're going to add the third atom, and things get interesting. Okay. So if I draw atom 3, that's also an oxygen. Now I've got 2 options, right? I can bond it to atom 1 or atom 2. what makes the most sense is atom 2. Okay, so we're going to say bonded to atom 2. What's the oxygen bond distance? It's a little longer than a H bond. We say what, 1.2? I don't know. We can give that as an initial guess, and then Gaussian can optimize the right number. So we'll say 1.2 angstroms from atom 2. So that's now the oxygen-oxygen bond length. Pretty easy, yes? But that's not enough to specify where that oxygen is in space. Because if you think about it, this is at the origin, this is 1 angstrom away, this is 1.2 angstroms away, but 1.2 angstroms could be over here. It could be anywhere in this circle. Right? And so we've got to specify the angle with respect to atom 1 so that we can pin it to a particular position. So the next thing is the angle with atom 1. Bonded to atom 2 at a distance, angle with atom 1. I don't know, what do you want to pick? 109.5? We'll say that these oxygens are sp3 oxygens. So we'll say 109. Any questions so far? So at this point we have, in our coordinate system, a hydrogen at the origin. Let's just say that it goes out in the y-axis. I don't know which axis it chooses. There's an oxygen. And then we've picked the other oxygen to be 109.5. Does everybody understand what's going on? This was 1.0 angstroms, this was 1.2 angstroms. Now can you imagine building your molecule, Jerome, using the Z matrix?
Oh, I can't
No, or even the benzene rings where you're going back around the ring and so on. It's difficult, but like I said, we'll see how we can make this useful in a second. Now we're doing the last hydrogen, hydrogen 4, bonded to atom 3. The OH distance is 1 angstrom in our case. Now we need to tell it an angle with something. So we have a choice. What angle are we going to use? Which, I mean, as far as which atom, it's got an angle has to be referred to a third atom. So we have a hydrogen bonded to 3. It's going to be probably easy to define that angle with respect to atom 2. So we'll put 2 here and 109.5 for the angle. But notice how this doesn't help us really nail down that last hydrogen, because 109.5 could put it there, but it's really somewhere on this cone. Right, 109.5 will get us to this cone, but this over here is also 109.5. You see the issue? I want to make sure everybody understands that this is, to this point, is not enough information for that last hydrogen. So what is it that we need to define? The dihedral angle is the last thing that needs to be defined. We need to define where on that cone this last hydrogen is. If we make it 180 degrees from this hydrogen, it'll be over here. If we make it 0 degrees to this hydrogen, it'll be over here. So we could do 30, 60, we could do anything with this last dihedral angle, and we'll pick a location on that cone. Okay? And so what we'll say is, we'll say hydrogen 1 or atom 1, and then we'll say, let's say 180. And these also have to have decimal places. So it's a floating point number, so it's 180 dot. So this means dihedral with atom 1. So let me do my best artwork and try to describe what these dihedrals are. Okay. So these three centers here, H1, H2, and H3, those are 3 points that are not on the same line. If you have 3 points that are not on the same line, they by definition form a plane. Right? You can have 3 points on a line, that's a line. But if you move one of them off that line, now you have a plane. That's important. I see some nods. Do I have everybody's nods? Okay. So that's a plane. So we're going to draw that plane right here. So this plane right here, I'll draw the plane of the board so it'll be square with us. Okay. So that's the plane of the board because all three bonds are showing that it's in the board. Okay. I'm going to draw this hydrogen with a wedge to indicate it's coming out of the board to us. Okay. Now let's look at 2, 3, and 4. Oxygen 2, oxygen 3, and hydrogen 4. That's 3 points. They're not on a line, and so they define a separate plane, a different plane. And so I'm going to draw that plane purple. Can you see that those planes are intersecting on a line and that they're at 60 degrees or something like that? You know, this is actually from this plane to that plane is like 120 degrees the way I've drawn it. So this is trying to represent a perpendicular angle to between those planes. Don't be confused by this wedge. That wedge angle is the 109.5. This is perpendicular. This is the perpendicular angle between those planes. Let's now draw this same picture looking end on. So kind of like a Newman projection. Let's do it this way. Let me draw it. So if you can see, I've drawn plane 1 here on that hydrogen and oxygen, labeled it plane 1. I've drawn this purple plane through that oxygen and hydrogen and labeled it plane 2. And the dihedral angle is looking down the 2 oxygens. So the oxygen-oxygen bond is, we're looking end on that. And this is the perpendicular angle between those 2 planes. The reason dihedrals can be tricky is because you've mentally got to see the planes of symmetry that are being rotated around. Now, the reason the Z matrix is a valid way to describe a molecule is it has the number of degrees of freedom for every atom that you need. The first 3 atoms have some assumptions built in, but from the 4th one down, you've got a new atom. How many degrees of freedom do you have with every atom that you add to the molecule? How many degrees of freedom for every atom? 3n, right? And so what is another way to think of degrees of freedom? Is how many things you have to specify to tell the computer or to describe where that atom is in space. And every atom has three items that you have to specify. Distance from another atom, angle with a separate atom, and dihedral angle with some other atom. So from atom 4 on down, you have to specify all 3 degrees of freedom. Yeah, yeah. Now the reason you don't have to specify 3 degrees of freedom for H1 is we stick it at the origin. So it's defined as the origin. The reason you don't have to specify the angle for oxygen 2 is it's by definition just stuck on one of the axes, Y or X or Z. Okay? And the reason you don't have to specify a dihedral for oxygen 3 is it's just, again, going to be in the XZ plane or the XY plane. So it defines some of the degrees of freedom for the first 3, but after that, you need to specify all 3 degrees of freedom for the molecule. The nice thing about the Z matrix, as opposed to Cartesian coordinates, is I can change this bond length independently. These are also called internal coordinates. So I can go and lengthen the 3-4 bond, the hydrogen-oxygen bond here, and guess what? I don't have to change the angle. I don't have to change the dihedral angle. It doesn't impact any of the other numbers in the whole Z matrix. Can you see that that's really fantastic? What if I wanted to scan the oxygen-oxygen bond length? If I'm using the Z matrix, I can do that. That's that number right there. And that number doesn't depend upon any of the other numbers in the whole set. So using internal coordinates is a really important skill if you want to find out how the energy depends upon a bond length or an angle or a dihedral angle. Because everything is independent from everything else. Think about the Cartesian coordinates, right? The Cartesian coordinate for atom 3, if I wanted to lengthen that bond length, I would have to change both X and Z, or both Y and Z to change that bond length. And it would affect this hydrogen too. So I've got to change the oxygen coordinates and the hydrogen coordinates just to move that bond length. So I've got to change 4 coordinates to scan 1 bond length. And I've got to do all kinds of trig, right? Cosine of this, sine of that, try to figure out if I want to extend it 1 angstrom, I've got the cosine of that angle, you know, times X and the sine times Y or whatever to get the distance that I need to move in X and Y. What a pain that would be. Really total pain. So working in Cartesian coordinates is no fun at all. So that's why the Z matrix is really very nice. So you may say, well, that's great and all, but I don't work with hydrogen peroxide. Okay? And so let's build in our molecules, let's build dichloroethane.
Do you know how to show bonds show when you make it through Z matrix?
Say again?
Do you know how to make bonds show when you make it through Z matrix? Like I was following along.
Oh, okay.
But it doesn't show bonds between. It shows like after distances.
I'm not exactly sure. There may be, sometimes I've seen some what do I want to say, some like menu items that say rebond the molecule. You hit it? It didn't do it? Okay, so I don't know.
Let's see.
Okay, so I'm pulling up GaussView as well. Let's just, so we've got carbon tetrahedral, so I'm going to click that, and I'm going to click one of those hydrogens, and that's going to make ethane. Okay, see that? It's nice. It's a good staggered ethane. And then, yeah, I'm going to come up here, periodic table, click chlorine, single. Yeah, that's the atom type I want, and I'm going to go ahead and make them, you know, trans. So opposite sides of the molecule. Now here's something that's fun. Let me switch this over to 6. There we go. Don't be bothered by the trippy background. You've got all of these little icons up here, and I tend to use the menu items because I don't necessarily recognize what the icons stand for. Okay? And what I'm looking for is I'm looking for the Z matrix editor. Okay?
It's in an atom list.
Atom list, okay.
Yeah.
Yeah, there we go. So the atom list editor. This is a really handy tool. Have you used this in your big system? You have?
Well,
Okay.
I use it, actually, I use it, no, more help me with my homework for GaussView.
Okay, okay. So this atom list editor, can you turn the middle switch on the 5 ones to hit that middle one? It's better, yes. Okay. And so one thing that's nice, come back over to your molecule view, okay? And with this screen active, come up to view and hit labels. So check labels. And then you can see the atom numbers, okay? So under view, you check the labels.
No, edit atom list.
Oh yeah, under edit, atom list. Got it? Okay, good. And so I'm trying to get a hold of my atom list. Okay. And so this is kind of the Z matrix format, only they've taken the bond angle and dihedral, and here are the atoms that we have. So when I have 3, 2, 1, those are collected over on the left, and then bond length, bond angle, dihedral are scooted over in blocks. So it doesn't exactly follow the Z matrix that you see on the board, but it works. Okay, so you can come in here, you could edit these numbers and so on. You've got the Cartesian coordinates over here. I'm going to go ahead just to simplify things and see up here it says show Cartesian coordinate columns. I'm going to click that and turn those off. And turn them back on, turn them off. So turn them off. Oh, this might be helpful for you. This is show MM types. So if you click that, then you get the MM type. So if you needed to change one of those, you could do that.
I don't want to charm, but yes.
Yeah, exactly. But at least you might be able to produce something.
Yeah.
And then the anion columns, I can't remember what the acronym anion stands for, but what it does is it allows you to put the molecule in layers. What is it?
Our own and something molecular mechanics.
Yeah. Oh yeah, we could. You want to Google it real quick? Yeah. And so what it does though is it allows you to take a huge molecule, and instead of calculating the geometry of that whole molecule at a high level, which would take forever, maybe never even finish, remember the 1700 years thing, to define a high layer. So let's say you have an enzyme and you have a pocket, and you want that pocket to be done at DFT level.
That's what we're doing.
Okay, so in the pocket, it's going to really model the electron cloud. Remember, molecular mechanics, there's no electrons. So how can you model the interactions in a pocket if you don't even have electrons? So you can define the pocket at the high level, that's what these levels are, and then behind that, maybe the rest of that backbone at the medium level, maybe do that semi-empirical, and then everything else, molecular mechanics. And the guy that wrote the software, think about this, the guy that wrote the software, the team, I should say, that wrote the software to allow Gaussian and other packages to do 3-level calculations, won the Nobel Prize. It's that big of a deal. So if you think about trying to take a huge enzyme that you could do easily with a CHEM or UFF, and then pick a region where you want to do at a high level quantum mechanics and have that connect, you know, the molecular mechanics and the high level calculation to each other, was important enough that they said this was revolutionary and worthy of a Nobel Prize.
That's what we're doing in the simulation.
Yeah, and so now we're doing Nobel Prize type work, or at least using that software here at SAM. It's great. Yes?
I
Okay, what is it?
Is our own n-layered integrated molecular orbital and molecular mechanics.
Okay, so yeah, it's the integrated part.
That's what it stands for.
Yeah, so they had to put the our own. It really should be union. Okay, so let's look at this Z matrix in the atom list and compare it to our molecule. And this is the thing, I guess, one of the main points. We built the molecule, but the way we built it is not very convenient for having the atoms be independent from each other. What I would like to have is the ability to rotate one group around that carbon-carbon bond. And so I don't want a lot of cross-bond definitions, okay? I would really like to just have one definition that goes across that carbon-carbon bond. So I could scan that dihedral and have both end groups referred only to themselves. So you have internal references and external references. And I would like the methyl group on one end to have only internal references. And then I have one dihedral, say chlorine to chlorine, that goes across that bond, and then the other end have internal references. So let me tell you what I'm talking about here. We have atom 1, which is a carbon, hydrogen 2, hydrogen 3. Notice atom number 4 is across the bond. And then we go 5 and 6, and then 7 is on the other side, and then 8's back over here. And I don't like that at all. Okay? I would like to define this whole piece first, and then this piece second. And so in this atom list editor, we can do that. Okay, so see this tag column? That's the atom number. And this chlorine down here that's labeled 8, I would really like to make that atom 4. So you can just double click that 8 and make it a 4. Well, backspace and hit 4 and hit enter. Okay. So notice it shuffled all the other atom numbers and updated our list over here. So this is great. I've got carbon, hydrogen, hydrogen, chlorine, and then it goes across the bond, carbon, hydrogen, hydrogen, chlorine. Did it work? Okay, that's great. So now I have at least the atom numbers, 1 through 4 on the left, 5 through 8 on the right. That's good. Now you can click this column, tag, click that column, and then hit this down arrow, and it'll sort those rows and move our chlorine up. And so hit the tag column here, and you can hit this arrow and sort them. That's a pretty helpful tool. All right, so now let's pick on our definitions. So this is hydrogen 2. Okay, oops, didn't mean to do that. And it is bonded to 1 with a bond length of 1.07. That's fine. Hydrogen 3 is bonded to carbon 1 with a bond length of 1.07. That's fine. Angle with hydrogen 2 at 109.5. So that's great. So it's just kind of like what we did up here with the hydrogen peroxide. Now here's where the fun part begins. So then we have chlorine bonded to carbon 1, bond length 1.76, angle with 2, 109.5, that's fine. And then dihedral with 3 of negative 120. Can we understand that dihedral? Okay, so let me draw the methyl type dihedrals on the board. Okay, so let's go over here. And okay. So let's pick, we have carbon, chlorine, hydrogen, and hydrogen, okay? And so what we have tell you what. This will make it easier to draw if I pick a different order. Here's what I want to do. Go back to your molecule since we have the Z editor open. So
Go to 5.
6. Now I'm gonna make it a little cleaner, I think, as an example. Okay. All right. Where's mine?
Yeah, he's mechanical. Yeah.
Okay. Let's do this. Let's define our backbone first. Okay. Let's do carbon 1 and carbon 2. So we're going to go find the second carbon here, and we're going to call that atom 2. And then reorder. Select the tag column and reorder. So that's kind of nice. We have our 2 carbons bonded to each other. The bond length, we could scan that coordinate directly. And now we're just sort of defining a methyl group relative to that other carbon. All right, so we have carbon 1, carbon 2. This hydrogen bonded to carbon 1 at the angle. And we're going to say angle with carbon 2. So this is nice. So this hydrogen is at an angle with respect to that carbon of 109.5. So that's kind of how you would define a methyl group. Forget that there's a chlorine on there, but we have a methyl group that we're defining. And then we have hydrogen 4 bonded to carbon 1, angle with carbon 2, 109.5, and then dihedral. I'm going to call this dihedral relative to hydrogen 3, and it's 120. So let's define this now on the board of how I'm defining these dihedrals. Okay. Carbon 1, carbon 2, hydrogen 3, hydrogen 4. And so what I've done is I've defined this angle here and that angle here. Both of those are 109.5. Is everybody okay with that? Now let's look down the axis. So looking down here, let's draw it. Sort of a Newman projection. And we have H3, H4. And then that chlorine up here is going to be 120 degrees dihedral. So this is carbon 1 and carbon 2 looking down, carbon 1 and carbon 2. And whenever you have something with threefold symmetry, you've got 2 dihedrals. One is, I would say, 120. Let's say the other one is minus 120 because it's going in the opposite direction. You have a 120 and a minus 120 to define that threefold symmetry. And that's going to be your typical methyl dihedral. Okay. If you wanted to convince yourself that this is still 2 planes, think about the 3 centers that define a plane. You have the 3, 1, 2 plane, and you have the 4, 1, 2 plane. And this dihedral is the angle between those 2 planes. And they share this axis of 1, 2. Yes? You have a question? Okay. And so that's why this dihedral over here is 120. Okay. Now let's do the chlorine, atom 5. Angle with 1, 1.76. Or no, distance to carbon 1. Angle with carbon 3. I'm going to go ahead and change that to a 2, since they're all defined as angle with respect to 2. And then I'm going to pick dihedral with 3. So we have plus 120, minus 120, just like I've drawn here. Everybody's okay with that so far? Okay. Now for the fun part. Okay. So now we have hydrogen, number 6, and it's bonded to, or hydrogen 6 bonded to atom 2, carbon 2 with this bond distance. Angle with atom 1, 109.5. So all of these should be angled with respect to atom 1. And then dihedral with respect to 3. I like to define the dihedrals with respect to the chlorine, just because the chlorine is an easy thing to visualize. There's 2 hydrogens, so it's hard to know which hydrogen you're talking about. So let's make this a dihedral with respect to the chlorine. Okay. So let's do that with this chlorine one. So this last one, we'll say that's a dihedral with respect to 5. And you see it pops up as 180. And I'm going to move this chlorine up in the list. I'm going to make this chlorine atom number 6. And I'm going to reorder them. And so now I've gone across the molecule and I've defined that chlorine with respect to atom 5. Then I put the last 2 hydrogens on. So this hydrogen bonded to carbon 2, angle with carbon 1, but I want this to be a dihedral with that chlorine, atom 6. That's minus 120, and we'll make this one with atom 6, and that's going to be plus 120. So what have we done? We've made the 2 pieces, the 2 ends of the molecule independent. This dihedral angle of 180 can be scanned, and when you scan it, the rest of the hydrogens will move with it. Okay, and that's the goal, is to have the 2 pieces of the molecule be independent. They can be defined across that bond with angles, but the dihedral angles, you should have only one dihedral angle that goes across that bond, and that's the 6-2-1-3 dihedral angle. So how did I get this 6-2-1-3, that designation, or 5, 6-2-1-5? It's atom 6 bonded to 2, angle with 1, dihedral with 5. So you can define those, that scanning angle is 6-2-1-5. So every dihedral will have 4 atoms that define it. Can we up here define these dihedrals using this designation? So this dihedral here is the 4, was angle 4 bonded to 1, angle with 2, dihedral with 3. That's the 4-1-2-3 dihedral angle. Atom 4 bonded to 1, angle with 2, dihedral with 3. This chlorine was the 5th element, so that's the 5th atom bonded to 1, angle with 2, dihedral with 3. Every one of these will have a different serial number, if you will, a different definition. But when you're looking at the output file, you'll have these definitions. It'll say dihedral 4-1-2-3, dihedral 5-1-2-3, and you'll be able to see what those dihedrals are in the output file. Yes, and that's how you cut. You can also find mistakes as well.
It'll tell you there's an A pair with this dihedral on 4-2.
Yeah, or collision. So what is the utility of this? Well, then when you get to the calculation steps, and this is what we'll do next time, you come up to the calculation. Wow, I don't know why it's going so slowly.
What hit?
Yeah, so then you can come up here and do a scan and it's going to give me a warning here. It says, and add scan coordinate using redundant coordinate editor. Okay. And so I had to look that up, and I want to uncheck this right connectivity for now, because that's, so under the general tab, uncheck that right connectivity. When it's checked, you see up there it says geom equals connectivity. If you uncheck it, it takes it out. Okay.
What does it do?
It gives you down the atom types and what things are connected to what other things.
It's not necessary.
Yeah, it's not necessary.
It's weird to figure that out actually.
Say again?
You were trying to figure it out.
Yeah. And so this says use modified redundant coordinates. And so how do we have to do that? It says use the redundant coordinate editor. So we're going to cancel this, and we're going to look around up here, and it says edit redundant coordinates. So we're going to click that. We get this nice little table, and we're going to add a coordinate, and it's going to be a dihedral. And this is where we put in those 4 designations. So we want the dihedral for atom 6, which is bonded to 2, which is at an angle of 1, and a dihedral angle with 5. And we're going to scan that coordinate. So in this list, you have all these options here, and then went down to scan coordinate. And we could take 36 steps at 10 degrees. So it's going to take that dihedral angle and scan it all the way around 10 degrees at a time. And it'll tell us the energies associated with that. We'll hit OK. I think I could pull this off in less than 5 minutes if I don't let it relax. So I have opt mod redundant. So job type, scan, and I'm going to say rigid. Okay. Ah, phooey.
Maybe it'll be relaxed.
Let's see. See what we get. Ah, it's not going to let me. Okay, so let me kill that. I did relaxed in my office. I'm wasting time now. And it took a little while. Yeah. Here we go. Cancel. Relaxed. Redundant coordinate.
We press Z matrix or we press relax and it gave you
Yeah, no, but I did that before and it gave me an error. So. We're running out of time. We'll have to do it this next time probably. If you want to try it between now and then, it'll be cool. I mean, how many people have access to Gaussian in their research labs or other places? It's in 321, isn't it? It's in all of those computers. So upstairs by the chemistry department, there's that computer lab. All of those computers have Gaussian.
Except for one.
One of them does.
Except for one. Okay. Okay. So we need to get that fixed. But try this. Try to figure it out, and that'll be actually good. So between now and next time, do that, and that'll be good for. In fact, struggle with this and get it done. That'll be this week's homework. Okay, it's trying to get this scan calculation to go. Just provide evidence that like do a screenshot of the results, and we'll talk more about it next time. Sound good?
You want the redundant relaxed?
Yes, I want redundant coordinate and relaxed, because what that will do is it'll scan the dihedral angle and then optimize all the other coordinates. And it'll scan it 10 more degrees and optimize all the coordinates. So that's really the best way to do it.
How long did it take you on yours?
I did a Hartree-Fock calculation, so no extra business on the theory, and I did a 321G, and it finished in under 5 minutes. Okay. So we could have done it this morning, but some kind of glitch happened, and now I can't get back to the editor. So
You're gonna post this?
yeah, I'm going to post this so that you can kind of go through and see what I did with the Z-matrix. And a lot of the Z-matrix stuff we did is not necessarily required for a scan calculation. It was also to teach you how to manipulate the Z-matrix. So that was really the main point this morning, was to teach you how to manipulate the Z-matrix. And then once you have some independent knowledge of the dihedrals, you can do a scan calculation. Okay. So if you'll do that as homework, then I will show you my results on Friday, and we can compare them. Okay? Sounds good.